Sorry. Hi, I'm Stuart. I'm a lead offensive security engineer, i.e. red teamer. And more importantly, I just sort of do Unix gymnastics from time to time. And also important to note, I'm not affiliated with any of the companies or whatnot we'll be alluding to in the talk. Standard set of disclaimers. None of these views are my employer's, past, present, or future. Also, if you're going to write the sort of things we're writing in here, please don't do that without thinking about who you're doing it against. And if you do, that's my name. Ich bin Mr. Strafbar. Cool. So that having been said, sort of a where are we type thing. This is us. We could be red teamers, pen testers, blue teamers testing tools, sysadmins testing the blue team's tools, really anybody else. More practically, we're the sort of people that see a Linux box and we're like, we have access to this thing. Let's run a thing on it. That sounds cool. And maybe the sort of thing that's an ELF binary, it doesn't really matter, but for this short amount of time, we'll just assume we're running some sort of ELF binary on a Linux box. Probably the sort of thing that maybe connects back to us and lets us do other things. The problem, of course, is that often there are things watching and things that are like, hey, is this maybe questionable? EDR or other things, network analysis, so on and so forth. EDR, endpoint detection and response, what we used to call antivirus. And that then, if it decides that we are malicious for some value of malicious, will go rat us out to a SOC analyst, or sometimes a sysadmin or whatnot, who will then have a very awkward conversation with us saying like, hey, what are you doing, buddy? Ideally, instead, this happens where the blue team tool is like, no, you're cool. That's not malware. Or alternatively, the SOC guy is like, oh, nope, that's a false positive. Or better, both. No, it's a benign program, no worries. And we'll be talking about small little changes we can make to hopefully make that happen. Quick plot twist. It is maybe not a common sentiment that, you're just like, share all the code you write, but I tend to do this with blue teamers who would like. I tend to go for things that the code will not catch, not sort of the security by obscurity, don't want my techniques burned model. It's just a little bit of philosophical rambling. How this all works, very briefly, each chunk of malware, each process has certain things that you can observe, argv, the arguments, or a file hash or something. That then gets sent to some magic box, and a vendor will tell you it's wizardry, AI, ML, behavioral analysis, take your pick. Often it's a static rule set, regex-based, or something like that. That then will turn into some sort of alert that says, oh no, the bad thing happened, holy cow, which again rats us out to a SOC analyst. The idea then is to change something on our side, to change some internal state of what's observed, the observing thing, to then change something in the internal state of whatever is observing us, to then change something in the alert, or maybe just prevent it from happening, to eventually just cause the SOC dude to be like, nothing, okay, that's cool. So then we can avoid those conversations. So setup we'll have for the rest of the talk for testing, very briefly, is some target. Our target will be a Linux box, completely boring, with notionally EDR that's less boring. We'll just write a little reverse shell as a thing to hide. Could be anything really, but for us, we'll just write a reverse shell with upload and execute via magic. I always hate to go to the talks and it's like, oh, here's a cool thing. And you're like, wait, 2 steps back. How did you get that on target? Demo magic. And we'll set ourselves a goal of stealing SSH keys, because we're stereotypes today. Here's our shell. It's a single function, single file program, written in Go. We'll start by connecting to our server, and we'll take oh no, where's my little, oh no, there we go, yes. I'll start by connecting to the server. We'll take our server address from the first command line parameter. We'll read a file, which we take from the second command line parameter, and send it back to the server with writing the buffer out. And then we'll spawn a shell, and we'll just hook up this shell to our network connection and run it. Pretty simple. Yes, it's plain text. We'll talk about that in a bit. And then on the receiving side, it looks like this. On this running side, it looks like this. We run it. We give it the address and port to call back to. That's the argv1 or os-args1. The file we want to steal, which is our SSH key. Listen with netcat. RLWrap is kind of neat, by the way. For those who've not used it, it gives you read lines, so lefts and rights and control use and all that good stuff, instead of just the typical netcat shell. And then, we get a call back. A call is received. We see our key has been exfilled. that we asked for, give it a command, process listing as one should when one pops a Linux box. Life is good. And then there are a few things that can get us caught. So number one is a scary name. And process names, for some value of name, anyways, can actually cause problems. I knew a young fella who was just transferring some files, and he thought it was funny, and he named his Python script lol.py, and the SOC was like, dude, what are you doing? You're not supposed to run League of Legends on your laptop. That was an interesting one. He's like, I don't know what. Our domain could be malicious. There are domains out there now that I cannot connect to as domains. Sensitive files can be a thing if this process, exfil in shell, was not a trusted process to open this set of files. That can trip alarms. And then plaintext TCP sometimes is watched if you have the right tools to do it. I had a conversation with the CTO once about whether or not I should be running shell commands on over the network. All right, so they say that nature loves to hide. We love to hide. And as we're hiding, a few things to remember. Not all of this will work in every situation. You'll find that sometimes, like, you'll think, oh, this will get past one tool and then another tool will catch you. But the flip side is, you probably only need one or two of these tricks, especially against Linux EDR, or something else. And then finally, the only real way to know is to try it, preferably with a sort of a purple team setup, not a, midnight, like, need to make screenshots and then somebody finds you. Not that I've ever done that. And then so for the rest of the talk, we'll start with a few silly little things, silly little 5-second changes you can make that actually do work. We'll spend quite a bit of time talking about argv, the command line parameters, and how we can change those. And that is the bulk of the way I've found myself in somebody's SIM tool. Talk a bit about network comms, how to hide ourselves a little with a minimum of work, not like super hand-rolled, perfect encryption, just like minor changes. And then a brief look at some system calls and how to avoid them, maybe. Cool. Oh, easy code changes. All right. So on these simple, silly things, you can fool EDR with this one simple trick. There is actually a vendor who was not happy to hear about this. So we take our thing we used. We see it's a couple mega file. Surprise, let's go. We can just append random bytes to it. And we can append 100 megabytes of random bytes. And we do that, and we see it's now 103 megabytes. And it runs just fine. And it turns out that everything that inspects a file has to have some limit on how much file it can inspect. And if you go over the limit, it just might ignore you. I'd love to take credit for this. I saw this in a tweet maybe 10 years ago, and I can't find the tweet, but to the guy who tweeted that, thank you. It helped a lot. TLDR, big binaries, not always inspected properly. Likewise, every chunk of data, you can take a hash with whatever hashing function, MD5 in this case. And you can also just append data to the file, the date and time, and that changes your hash. And now you suddenly have a different variant of this strain of malware. Totally undetected, never before seen. You'll know that you're getting detected by hash if your thing takes a couple seconds to start the first time, and then the second time, it's either really fast to start or really fast to not start. That likely somebody is checking hashes against some database. And that works. And then third trick, different hash, different malware, sorry. Third trick is a way to fool sandboxes. Not that I usually worry about this, but I sort of accidentally found this one day. I really just got lazy and forgot to check the length of the command line arguments that I passed to myself, really. Missed one, didn't remember to type it, and then my malware crashed in the sandbox. And the sandbox was like, oh, you didn't do anything malicious. Cool. Perfect tool. Definitely not blasting SSH keys out everywhere. So, argument vectors, the command line arguments you type in are probably the number one way I've found myself not being undetected. Briefly, we have our command we typed out, looks like this, and we can ask this file, proc pid command line, hey, what are the arguments? And it's obvious, right? It's like 3 of them. There's this one, and then this one, and then this one. And yes, the file, by the way, is null byte 0 separated, not new line separated. So we'll just translate new line or nulls into new lines. It'd be easy. And we see, yes, sure enough, we have 3 arguments. Okay, this is pretty obvious, right? And this is what it looks like if we do a process listing. I had a very long conversation with a friend of mine who's a SOC analyst, like, hey, do you look at it like this or like this? And he's like, no, actually, usually when I do things, it's just one string. We regex on it. It works. So I'm like, oh, that's a pretty good opportunity. Some observations. Regex-based detections are somewhat common. Unless you're talking to a salesman, they're very common. And argv0 is taken fairly seriously. That's a lot more faith is put into that. That lol.py thing. I once ran something and I called it port scanner. It was a port scanner. I ran a port scanner. We got a message back from somebody. I forget what. It was like, there is port scanning on your network. It's bad. And it turns out they just saw the word port scanner as argv0, and that was enough. If you want to test this in a situation, try running curl with something that gets caught. Curl downloading a shell script, piped sh or whatever, and then try copying curl to girl. And I've done this, actually. And it worked pretty good. I also knew a young lad who just was like, okay, here's what we'll do. We'll just make a list of all of the bad commands and find you that way. So if we can get around this argv0 thing, we'll probably win. And we laugh and we say, oh, wow, man, can they really do that? And well, you get on a box, list the processes, make sure they're not going to catch you. How often do you dig into those? So it does go both ways. And aside from argv, there are many other ways to get your runtime config, get you what to call back to, what file to grab into your program. That's sort of where we'll go with this. Easiest way then is just to bake it into the source code. All the programmers are like, do you have to hard code things? So this is what we did. And we have our arguments 1 and 2. 0, of course, is the name of the program. Asterisk for later. And we can just change that nicely. Set a couple variables at the top of the file because hard coding is not that great. And then just stick them where we would have stuck things from the command line. Compile it. Cross-compile it, by the way. Go compiles nicely. It's a BSD box we're using. And by the way, for those using Go in such a context, trim path is nice. It gets rid of the bits of the path that have your name in it. And we'll set some linker flags, specifically main.address, which is why we stuck this in a variable. So that at least at compile time, we can configure it a little easier than having to edit the code every time. Set it to the address that we want to call back to. Same with the file. And then we can just run it. But we can also run it and stick whatever we want in there. And now we can be like, oh, no, these are benign arguments. We won't get caught. And we can look and say, yeah, actually, that does hide us nicely. TLDR, argv in source code means there's no argv to regex on, which is great, except you have to recompile every time. So easier maybe is we'll pass it in from the environment. We already used the environment a bit when we compiled our thing. We set the environment variable GoOS to Linux. And we can do this fairly simply in code. If we take, this, what we had, and just add some space and add an environment variable. Okay, we'll just look for underscore address. Why not? And we will grab that key value pair, the value in that key value pair, and try it. And if that's unset, compare.or will default us to address, which will get stuck into the address, i.e. this thing, and passed on. We can do the same with the file. Works nicely. Building it, now we don't even have to worry about coding linker flags. And running it is exactly what you'd expect. Stick the address in the address, and that will get stuck where it goes. Stick the file in the file, that will get stuck where it goes. Run the program. And it works nicely. We don't have to worry about our command line. The downside is we can look at the process's environment and find out that, well, okay, it is still a little visible, but perhaps less so. It's friendlier to use, and it's less noticeable. Of note, EDR, well, not much is going to see this in a command line. Well, I'll see you running the command. Not really. Cool. In that case, let's just take the arguments from standard input, argv in air quotes, from standard input, so that way it's not in our environment variables list. So that's what we were doing. We'll add ourselves a little space, and then we'll use format.fscan, which will scan a file, and the file just happens to be standard in, and stick the first word, space-separated word in address, the second in file. Do some error checking. We'll ignore end of file. We'll ignore there is no more standard in, because that way we don't have to set a file. We can just set the address, or set neither of them and default to the environment variables or hard-coded values. Error handling. There's a few ways then we can get data into standard in. The obvious answer is just echo it in, with the obvious problem that now you're back to things on the command line you would rather not be. Looks like that, of course. If you have bash, you can use, yes. If you have bash, you can use a here string, not a here doc like we're used to, but a here string with 3 left angle brackets, which is the nice benefit that it's no longer in argv anywhere, and it's no longer in a file or whatnot, with the downside, though, that you need bash. which is not always guaranteed, especially in containers. Of course, you can just use a here doc as is easy. The downside for that, by the way, is it will make a very temporary file. I think the file is made, then unlinked, then written to, but still there is a file. Cool. TLDR. It's not even in proc pid environment, but it is kind of annoying to give up your standard in if you're writing a typical Unix filter type thing that you've uploaded to your target. So we'll just take it from a file descriptor. That's not standard in. It's almost exactly the same. So we have standard in being read. And we'll, instead of doing that, define ourselves a file descriptor number. And standard in, by the way, is just file descriptor 0. That's all it is. And we'll just roll a new file abstraction over a file in the Go world with whatever file descriptor we set. And pretty much everything is going to be the same, except we'll also just not worry if that file doesn't exist. And that way we can be like, config if we want it, no config if we don't want it. Cool. And then using it is almost exactly the same, except you need to put a 7 in various places like that. And it works. TLDR. We can take a non-standard in file descriptor and use it too. There is argv0, and I would like to point out there was a recent blog post about this that generated some noise online. I wrote these before that blog post, for the record. Much like we're not pooping on anybody's EDR product or network traffic analysis product, whoever, not pooping on anybody's blog post, for the record. Anyways, we normally run a program like this, and we get argv0 is the program name. You don't actually have to do that, it turns out. If you have bash and I think Z shell, you can say, hey, make whatever I give you argv0, which also answers the, is this really the process name question? And we can say use cargo pants. Why not? That is our argv0 now, plus the program name to run, and then whatever other arguments. And if you look at the command line, now you have what you've set, and you've taken what looked like malware and turned it into what looks like malware. The collective groans of pain. Anyways, easy change. Instead of our new file from file descriptor 7, we use a buffer with our 0th argv0. One of the nice things about Go, by the way, for writing this sort of thing is that you use a lot of interfaces. So scanf takes an io.reader, not a file actually, which is really just any type that has a read method defined on it. So you can swap out things, much like you go to the mall, you swap out your flip-flops for shoes or whatever. You can swap out a file descriptor for a buffer. Sure. Looks like this. Exactly what you'd expect. Now argv0 has our two little things we've been configuring this whole time. And then our command line, argv0 has a space. That's okay. And then if tooling gives the SOC a single string for here's the command line, it does actually kind of look differenter. If we look at a process listing we grep for our program, it's not there. Look at a process listing grep for our domain name, it is there. But just looking at this, and I would do the same. It's like, oh, 2 arguments. Not really. You can still find the program, by the way, the actual binary that started it off with procpid.exe. And it looks like that, highlighting because colors did not show up very well. TLDR, you can use argv0 for argv for your input, but really it's like, don't do that. It gets kooky. Okay, so network comms. As I mentioned, I had this discussion with the CTO at one point in my life about like whether or not I should put certain things on the wire. If we look at ourselves, this is about what we look like if we take a packet dump with TCP dump. We see that, you see the connection, you see the private key, which is maybe not great as well. You don't really want to put your company, your client's secrets in the wire in plain text. We can see the command we ran and the output. So it's very visible to anything doing deep packet inspection. And so we can just encrypt this to make us invisible. You could write your own encryption if you really want. I wouldn't. I would instead I think I counted 8 different characters changes, TLSify everything. And now we are invisible. It is that different, that easy to make the change. One of the things I love about all this is like 8 characters on our side change is like, oh no. And I remember when TLS got easy, like when Let's Encrypt came out and so on. And there was a big like, oh no, what do we do now? That happened. Of course, you need something to catch the TLS connection, which means you need somebody to generate you a cert, or you use self-sign one. In the code for all of this, there's a GitHub link earlier. We'll have it again later. Little program that will grab you a TLS cert and catch your connection. Cool. So less than 10 characters changed. TLDR adds TLS and maybe invisibles us, but only sometimes. Sometimes you have either TLS man in the middle, which I guess we call TLS intercept if we want to sell things. And that can be a little problematic. At one point I was working at a place and they're like, okay, SSH is bad. SSH is used by hackers. We're not allowed to SSH. No more SSHing. And so I did the logical thing and I just wrapped my SSH in TLS. And then I wasn't SSHing anymore. And then somebody decided, oh no, we need to man in the middle all TLS connections. And I was like, so I just wrapped it in HTTPS. Just added a HTTP GET and then SSH. Changing to do that, not terribly hard. It's a little bit more work, but we'll use a nice pipe. It's an abstraction. You stick things in the write end. You get things out of the read end. Not terribly much different than a Unix pipe. Our connection now is no longer net.dial, but http.post. We'll make a post request because post requests normally have large bodies, or can anyways. And the body will come from the read end of the pipe. Cool. And then sending back the file which we've read, we just stick it in the right end of the pipe. Now our file goes into our post request and to the server and printed to our screen. And then shell will spawn. We need to get things back from the server. So that's the body of the response. The post request response is from the server. And output from the shell will go back into that same pipe. So fairly, simple 2-minute change. And now we have HTTPS. You also get the nice benefit that you can go through a proxy because Go's HTTP library sets proxies. I think a lot of them do if you set the HTTP or HTTPS proxy environment variable. Also means that you can use sort of cloud-based load balancers. I got sick of my domains being burned at one point, and I was like, okay, I'm just going to use whatever cloud provider's API gateway type thing, AWS, I guess, API gateway, because nobody's going to block that. Worked nicely, all HTTPS. TLDR, to use a not malicious protocol, it's actually pretty easy. Another single-digit-ish minute change. We do still have the problem, though, that DNS is not encrypted. I mean, yes, it can be, but we'll assume for the sake of argument it's not. So the simple answer there, without going terribly deep into it, is just don't do DNS. In Go, this is how I would tell the HTTP library if this environment variable is set, which was defined somewhere above, you can believe me. If that's set, okay, then we'll just make a function that dials an address and port and stick that into our dialer thing. Actually going through and reading the logic behind this is a little boring. So we won't do that, but take it for what it's worth. TLDR, you can avoid DNS detections by avoiding DNS. Last thing, we'll talk about system calls that are malicious. For somebody's definition of malicious, file opens actually is one that I found I was not expecting, but there are things that are like, okay, this process and this file should not go together. As a sort of what it looks like under the hood, we'll take cat and we'll read the SSH key we've been going after the whole time, and we'll run this in bash with strace so we can see the chain of system calls, at least the ones we're interested in. And we get bash starting, sure. We get cat starting, as expected. We get an open, as expected. And from anybody looking, we have cat opening a file, which is exactly what happened. And we can avoid this with one simple change, file redirection. So instead of cat opening the file, if we'll do our nice Tracy thing again, we have bash starting. We have bash opening the file and then starting cat. And this actually is, in real life, how I typically read files. I just add a left angle bracket, one of these, and I just don't worry about it anymore. It's quite nice. We can put that in code to have code take input that way from standard in. By instead of reading the file into a buffer and writing it to the pipe from our HTTP thing, we'll just copy from a new file from whatever file descriptor we choose to that same pipe, error handling. Looks like this. Chose file descriptor 8 just because. And instead of read from file descriptor the program opening the file, it will read it from a file descriptor. If we look at the system calls, we have bash starting. Bash opens the file and changes it to file descriptor 8 for us, and then starts our program. So as far as anybody knows, we didn't open any malicious file. We're just reading. Totally cool. Let the shell open files for you. We'll save a little bit of work, a little bit of conversation, more than work. Without going into details, at one point, I was helping with an incident. I'm a red teamer, but every so often they're like, hey, red teamer, what do you think about this? And the question was, hey, how do we take this process that we're interested in and see what files it has open? And proc pidfd is the obvious answer. And you kind of want to see something like this, which means that it has no files open and presumably is not reading your SSH keys, which we've also seen is not always reliable. Instead, we actually saw something like this. Of course, this is not real life. And we're like, oh, that's not great. sudoers is open for reading. Whatever it was in real life, I couldn't even tell you. So we would like to maybe not be in this situation. And the answer is to map the file into memory. You'll still have it open for like a second, but if the incident is being responded to or whatever, not such a big deal. Also for the EDR out there that pulls proc and instead of using netlink or whatever, it's like, hey, let's just look at proc every second or something, which happens. You can win that race. So a map file in memory, it looks like this. We'll start with that same thing we've been doing. We'll send a file into file descriptor 8. This time we'll send a whole hard drive. So this is a disk, VDA. And if we look, yep, it is open. It's open for reading. Nice. Exactly what you expect. All the other things are open. Sure. And the core of it is we call mmap and map it into memory, the file. For reading, share is nice, just takes less work. Error handling, we need the size. We can get the size just by seeking to the end, figuring out how big it is. By the way, if you're dealing with proc, they have a 0 byte size often, so don't use stat, use seek. Many minutes of my life were spent trying to figure out why I wasn't reading. And then it looks mapped, and procpid maps will tell you what's mapped into memory. Normally it's your binary, the shared object files, should you have any. Go doesn't use any on Linux. And it is still visible, but hopefully less likely to be seen. Close the file descriptor, of course, and then just for the sake of something to do with it, also because that was our goal, we will use some regex, which I would define like above in the code. We use some regex and just grab, through that buffer that we have mapped, we'll grab all the keys and just print them to our writer, our pipe going back to the HTTP server. Don't forget to unmap the file, by the way. Output looks like this. Got a callback, got the connection. We do see that we found a private key that we scraped off the disk. In real life, you get a lot, and it takes a bit. But it is a nifty way to, once you have root, figure out all of the keys deleted and undeleted. TLDR, memory mapped files, are easier to use because you don't have to deal with reads and figuring out how big your buffer is and should you need 2 buffers because you might have something on the split or whatever. And maybe not noticed. Fork and exec also gets caught. I mentioned I was like midnight making screenshots, and what got me caught was changing a timestamp. So if we look at just this program we'll be using, we can see that September 9th, it was written, root's home directory was written September 7th. So assuming I was on as root, hey, something happened in the past couple days. And I did something similar to this. I touched the timestamps back to whatever root was. So it would look like this, hey, no, this wasn't since whatever you're thinking of responding to. No, this was old. And then somebody was like, hey, buddy, what you doing? And turns out something was like, oh, hey, touch. It was a regex thing, touch with an R with a process or not a process, a program name. Whoops. And the simple solution is just to write our own code to do that. So we'll use change times, and we'll touch ourselves. os.arg0. I'm sorry, that was not actually a joke for the gentleman in the front row who's still snickering. We will change our own timestamp, and we'll just change it to a week before, a negative offset. It looks like this when you actually run it. So we'll list we started at September 9th, run the program. It changes its own timestamp to September 2nd. One of the quirks of using arg0 as what to change is if we have another file there, say xfill and shell, which was written slightly after this, so presumably from, in the minute after we landed, we uploaded something, sure. We can use that exec-a trick to set argv0 and change the timestamp of a different file. It's kind of neat. TLDR, syscalls may be less catchable than external programs. Last thing is, as I alluded to, shells get away with a lot of things that you're not meant to do. I've seen rule sets that's like, okay, this is not supposed to happen unless it's sh or kshell or bash or whatever. We'll look at the interesting bits of this. And what we'll do is we will inject ourselves into the shell so the shell is running. So it's like I said, I had this program named port scanner that was a port scanner. And the SOC was like, no, actually it wasn't the SOC. Something else was like, oh my God, port scanning. What they didn't catch was that the shell was also port scanning. Obviously, Z shell should be port scanning things. They also didn't catch portscanner.c next to it. But anyways, and this is sort of how I did it. You have to write slightly differently. If you're going to inject, the easiest way is to start your business end of the code in some initialization function or constructor function, and just have that spawn a shell. So in Go, it's Go space, or it's not a shell, I'm sorry. Have that spawn a thread, Go space something, and it'll fork a thread and do its thing and leave your victim process to go about its merry way. Of course, you also might want to run this as a standalone program. So main is what starts a standalone program. It can't just call the shell as well, because now you have two from your init or constructor function and main. You don't want to do that unless you do, or maybe you do. I don't know. And the easy answer in Goland is to use a context which gives you two things: a cancel, a cancel function, which then says to anybody watching the CTX variable, "It done." Looks like this. Our shell will just, whenever it's done, hit this call this cancel function, and then main will watch it. So that main won't exit before your shell is done. Several hours of my life went to figuring out why my shell called back and then died very quickly. And then the last bit is you don't always get logging like you expect. You can't just write to standard out, because who knows what standard out is what your parasitized process's standard out will be if you're not in a shell anyways, which we won't be in a second. So just open a file. Log is set somewhere. Sure, open a log file. The catch with the error handling is there's not really much you can do if it doesn't work. Kind of the whole point is you can't really get output very well, so just bail. Another quick trick, stick the PID in there in your log messages if you can. It helps for debugging quite a lot. And so then when something goes wrong, you can, instead of log.fataleft die, or however you die, stick it in the log file. Preferably a file that nobody's going to notice. Using it then is not terribly different, compiling it, not terribly different. The only catch is you can't really cross-compile very well when you're doing this kind of thing. It's a little different. So my Linux build box just has an NFS share for all my source code, so we don't have to deal with file transfers and such. We'll build it more like we'll use for our file proc self command line, so we can see what we're injected into, make sure we got that right. And then to build a shared object file, we can then shove into things, build mode C shared. Cool. And that gives us now a shared object back. Good. On the business side of this, we have injectlib, we call it, .so. We see it as a shared object file. And in bash, the enable command will enable a shell built-in from a library. And if you don't give it a shell built-in name and a library name, it'll just assume that the built-in it should call is the same name as the library. I always end my shell built-ins with .so. But anyways, and it'll whine at you that no, it loaded this library, but there's injectlib.so struct or something. It's not there. I can't enable this function for you. You messed up. But it did load it, or open it at least. And so yeah, we got a shell back, and we see it's -bash, not the binsh, what we'd sort of expect. If we grep around our own shell's PID, we'll see that, yeah, there's the shell. Well, there's our PS and our shell, but its parent, what it's running in, is bash. And a nice little side effect, if we look at our network connections, it's bash, not binsh, that bash, that made the network connection. So our super scary shell here, and it does not have to be a shell. You have bash do whatever you want, like my port scanning. Not making a network connection, nothing to see there. TLDR, inject code into known not malicious processes. Shells get away with a lot. EDR gets away with even more. I did this once in a test environment just so I could say I did, but it works. You can totally just shove things into EDR as well. Most processes do not have a user callable, please load my library. But if we just happen to have GDB, happen to have GDB on target, we can ask GDB, we can hook it up to whatever our super duper EDR is or other victim process and just say, hey, please call this libc function to open a library. It will, hopefully, it'll whine at you, but it'll still do it. And yeah, you get your connection back and you can see, yes, we have in fact parasitized our super duper root proof EDR. Super duper injection is super duper. So that was cool. What just happened? TLDR, to all the TLDRs, number one, Linux EDR will, and other things, observe a very finite set of observables. Regex is probably regex and argv specifically, probably the number one thing to worry about. And then we can get around that with fairly small code changes that on our side are just not a big deal. But on the other side, the people watching us can actually make a really big, like, oh no, that is completely difference. And third thing, do it. There's only one way to know if it's going to work is just to do it. Thanks. Do we have time for questions? Yes, time for questions. And by the way, that is me and the link to the source code for all of this. And my apologies to anybody who tries to read the make file. Sorry. All right. No questions. Oh, I'm sorry. Wait. I lied. There was a gentleman in the front row still snickering and totally distracted me. What's up?
That was terrifying for me.
Oh, good. I'm glad.
It struck me that even like loading for certain syscalls, not share everything is demonstrated. How much do you find programs pick up?
I have never sat and say, okay, this not technique our side, but technique your side will catch this. And actually, when I was originally thinking of this talk and putting it together, I was like, oh no, I'll just find all of the open source products I can and like compare them. Like, that's not really a nice thing to do. Like, so short answer is I have no idea. Long answer is from somebody who just gave a talk about BPF, you're like, so.
Your memory mapping would be called by longer. The open syscalls, you have to run the LK reader,
Yep. Yeah. And that's, for every defense, there is a countermeasure. For every countermeasure, there's a countermeasure. Totally depends on where you are, which is the last bit here. The only way to know is to try it. Yeah. Good question, though. Sorry, I don't have an answer. Any other questions and or Snickers? All right.